In the last 3 episodes of this series, we've looked at some basic experiments showcasing quantum mechanics, we've developed a basic understanding for quantum reasoning, and went a bit more in depth into the mathematics of the wave function. And in this video, we'll take this wave function and turn it into a wave vector? Well, yeah, this integral may seem scary and the other integral doesn't make it any better, but by the end of this video you will understand the both of them and where they come from. So let's get started right away with So first, a quick recap. What is a wave function? Why do we need a wave function? And what is a wave function? So, what is a wave function? Well, particles behave as both waves and particles, meaning that they seem to exist as a singular point in space upon measurement, but the underlying mechanics guiding the probabilities of these measurements treat them like a wave. So the laws of physics basically treat them like a wave until we measure the particle, and then this measurement forces it to become a point. So the probability of what the particle will be is dependent on a wave, but the effects of the particle are like a point. And so this wave function is just a function describing how these laws of physics affect the particle. Second, why do we need a wave function? Well, it's because when we do figure out the wave function of a particle, then we'd like to do a thing for which all of physics was created, and that is predict the future. Now obviously you won't be able to predict it perfectly, since quantum mechanics is probabilistic, but at least we'll know where the particle is most likely to be. And then, the third question. What is a wave function, this time from a mathematical point of view? A wave function is just a function that's a complex wave. There is one more thing I forgot to mention in the last video, that has to be square integral, but I mean, that's kind of obvious when you think about it, so I won't
this side, Larry. But
now, the goal of today's video,
me on a bad day,
will be
drunk
to turn
apparently
this wave
back
function
there.
into this wave vector? What is that even? But before we get there, let's talk about the difference between scalars, vectors, matrices, and functions. So what is the difference between them? Well, first, as a quick overview, let's start with scalars, otherwise known as just numbers. It's the thing you use for counting apples or oranges or rotations on the complex plane. It's just a number, but since I'm trying to extend the runtime of this video as much as I can to get that sweet rent money, we should explain it a bit more by talking about fields. So, what is a field? Well, there is a bunch of different fields. In the previous video I've already mentioned the physical field, which is different from a mathematical field, not to be confused with the field of mathematics or the field of physics, or this field that we're standing on this random sculpture, no. Today we're dealing with fields in mathematics. So, what is a field in mathematics? Well, first let's clear up the confusion, because trust me, if you're researching theoretical physics, it gets pretty gosh dang confusing. So a field in physics means that you're taking some kind of space and assign a different value to each point, right here represented with brightness. So when you hear the electromagnetic field, that's what it's referring to. A field in our space where each point has a different value representing the properties of electromagnetism at that point. So right here, the color of each tiny sphere represents positive versus negative charge, and the size would represent the magnitude. It's oversimplified, I know, but I'm just trying to give an example. In mathematics, however, a field is just different kinds of numbers. Explaining the topic in depth is a story for another time, but here's the TLDR. A field is a set with addition and multiplication defined, and by extension subtraction and division, in which these operations on any two elements in the field will also result in the element in the field. So for example, fractions. A set of fractions is a set in which if you take any two fractions and add them together, or subtract them from each other, or multiply them together, or divide them by each other, all of those things will just result in another fraction. As such, rational numbers are a field. Another example of a field would be algebraic numbers, or real numbers, or complex numbers. All of those are fields. But to solidify our understanding, let's imagine something that wouldn't be a field. For example, integers. Now, integers do fulfill the requirements I've mentioned so far. You can add and multiply them, but there is a bit more to it. Another requirement of fields is that for each element of a field, there has to exist another element that, when it's multiplied by, it returns to 1. So for example, with fractions, if your number is 2/3, then the inverse would be 3 seconds. Simple. But what about integers? Well, when it comes to integers, you can see that if we have a number like 3, we need to multiply it by 1/3 in order for it to get back to 1. which we can't do because 1/3 isn't in our integer field. And
See,
as
again,
such,
it's that
integers
7,
are
5
field.
over 7, which is
Another
1.
even simpler example would be
There's,
integers cut off
I'm really not
points,
sure
so
about the
integers from
math,
1
the
to 3, for
geometry
example.
to pump
In that
out
case,
the
showing that this
number
in a field
of
is
saying,
easier because 3 plus 1
if I'm
equals
doing
4,
log 10,
which goes
but
outside our
again,
field.
log 5
And so
over
those are the fields in
f7 over
mathematics.
7
Now, these
and
fields
the
are important because if you have some kind of function,
is
transformation,
the
or whatever else you could possibly have in mathematics, it's convenient to talk about it in
like
terms of the
you
numbers
the,
you could plug into it. So, for example,
arrow
this
keys
equation
in a
will
bracket,
always return
not
a
necessarily
positive real
greater
number
than,
if x is not
because
equal
it's
to 0.
squishy about whether that's going to be a
Only if we're
line,
dealing with
and
real
therefore
numbers.
it's a
If
triangle
we're dealing
die,
with complex numbers, then the
which I'm
story
not sure what
changes
it's
because we
called.
could just square I and get a negative
And
1.
so you
And
get
that's
that
how you work with
scalar
single numbers in
field,
mathematics.
rise
You don't
over
want to
risk,
work
risk
with any
over
specific
strategy
number,
of
and
rise
instead
over
you like
risk,
to
and
describe the properties
honeycombing
of fields, which allows you to
gets
specify the
into
properties
some of
of
that
all
issue
numbers in a certain way,
geometry-wise, so you
and this is
can
very
use it
convenient.
that
Now, with that
way,
in mind, let's move
but
on
you don't
to
need a dice to do
vectors.
this game,
So,
you just need to
what
keep
are
track
vectors?
of the area
Well, I won't
under the
spend too much time on
curve,
it because
what
vectors
is
are
the measurement
basically just
of
multiple numbers.
that's
That's really kind of it.
the age
A
of the
while back
universe.
ago, I made an entire video about
Kind of
this
some Klein bottle
precise
stuff here.
concept, so
Again,
I
it
won't
doesn't,
really
scaling
overdo it
wise, you
again.
could
But there is one thing I'd like to
argue
focus
it's
on, at least for
doing
a bit,
what
and
it's
that's the
supposed
fact that you can have vectors made up of different kinds of numbers. And right here, the notation for it is rather nice, whether it's a 3-dimensional real vector space, or a 2-dimensional complex vector space,
Well, because
or a
what this
whatever
is,
dimensional
could a
whatever
drone
field
repair
over whatever vector,
facility,
whatever space. The
Boeing
point is you can create any kind of vector space over any field.
F-14
And as you can
military
probably tell,
contract,
this would be especially
because
convenient
you
in quantum
can.
mechanics, considering how when we talk about the wave function, the complex aspect there is quite present. Next, there are matrices. And so, what are matrices? Well, technically, matrices are really, really simple. Just like vectors are columns of numbers, matrices are like rectangles of numbers. But
and then this thing will dance around.
Because have you ever wondered, why do matrix transforms look the way they do? Well, if you have and you'd like a graphical representation, once again...
Play the game. Play that game right now.